Wasabi, you guys. Welcome to Integration Bee Training for Advanced. This is part 16.5. In this section, we're going to be learning about limit substitution. So this is where the fun stuff and the nastiness begins. Just a little nasty, but this is where it gets just a little bit trickier. Even though it's a limit substitution, it sounds fun. It's still an advanced move to get used to. Okay? So let's go ahead and start with a concept first and show you what I mean by a limit substitution. So there are some times where we have a limit integral where we get something like this, an n, and then let's say from some bound a to b, okay, and then you're given some weird disgusting integral like this that has nothing to do with limits, right? It's just a bunch of x's, but it's like a non-integrable function. But then you have this limit n here that's going to infinity. And so it's like, what do you do? What on earth do you do? Right? So, in limit substitution, we take advantage. So pretty much we're doing a u-sub, not because of a function, but because of a limit. So in this case, I would, for example, this is the most common case, let u equal x to the power of n. And the reason why I'm doing this is because when I do du, I get n times x to the power of n minus 1. So this n is going to get rid of this n here. Okay? And then you're probably thinking, okay, but what about x? X is equal to u to the power of 1 over n. And what's 1 to the power of n? 1 to the power, to the power of 1 over n. What is 1 over n? N is infinity, so plugging infinity, this is 0, this is going to equal to 1. Mind-blowing, right? So, this is a trick that we would do a lot, but it's not very comfortable sometimes. So, let's say x, we have x to the power of n minus 1, but x is equal to u to the power of 1 over n. So n minus 1. And then here we have 1 plus x. 1 plus x is u to the power of 1 over n. And then f of x of u to the power of 1 over n du. And the n gets cancelled out. So this is what we have left, and so when we plug in our limit, we are left off with, well, again, u to the power of 1 over n, this equals to 1, so we get f of 1 du, this is what? U, this is 1 minus 1 over n, so we get u, and then 1 plus, let's see, this is 0, 1 plus 1. So now this is I don't know, however you want to, if you want to define this as ln of b over a, if that's how you want to answer it. Yeah, in a way, pretty much. But this is just an example, right? You're not always, it doesn't always going to look like this. But this is a very common example that we will be doing a lot. Let u equal x to the power of n. Not because of some function inside the integral, but because to get rid of this n here. Okay? Alright, you're already feeling the adrenaline already. You know how exciting this section is going to be. Alright, let's finally get to the examples. Okay, so we have this limit integral here. We see x to the power of n, but it doesn't seem like we need to domain split because we have from 0 to 1. However, we have an n here. Interesting. So there's something that we need to get rid of, especially this n here, because that's infinity multiplying this whole integral. So we need to get rid of this. We need to get rid of that. So how do we get rid of that? We can let u equal x to the power of n. And du is equal to nx n minus 1 dx. So let's go ahead. To find what this is, well, we need 1 over n equal x, and so the derivative is going to be 1 over n u 1 over n minus 1 du equal dx. So this 1 over n is going to cancel out with that, Okay. xn is going to be u. Dx is going to be u 1 over n minus 1 du. And then we have 1 plus 1 over, u to the power of 1 over n plus u. Okay, this and this cancels out, and so we're left with this. Okay, plug in infinity into n, and we get 0 here, 0 here. We are left with u to the power of 0 is 1, so we have du, and 1 plus, and then we have u to the power of 1 over n, 0, so this is 2 plus u. Okay, so it seems like we have ln of 3 over 2. And I believe that is our answer. Okay. So now we have another example where, it's the same old thing again. We have n at the front. So we need to get rid of that. Okay. So let u equal x to the power of n. Then x is equal to u to the power of 1 over n. Dx is 1 over n, u 1 over n minus 1, du. Okay, so we get rid of that n, and then here x to the n is u, times dx is u 1 over n minus 1, which is what I like about this whole thing. It cancels out. Du 1 plus x squared is now u to the power of 2 over n, which will not matter because this is infinity, so this whole thing is going to equal to 0. So we're just going to end up with 1/2. So I believe this integral is equal to 1/2. Okay, look how quick we solved that. Okay, sometimes I think the original method, they did integration by parts, but you see, I'm lazy, so limit substitution is just a lot quicker to solve. Okay, so definitely limit substitution is highly recommended. We see that we have n at the front. Well, I mean, not exactly in the front, but right here. And then we have the sign of e to the x, whatever this is. Like, what is this? So, what do we do? Right? Do I just, okay, we have n and then we have u. Okay, we're just going to do this limit substitution? No, not always. Not always. I only let x to the power of n because it's just common and easier. However, we don't do it here. Okay? It's not the only substitution that gets rid of that n. We can also let u equal nx. And it also helps us get rid of that n as well. Okay? The reason why we don't use this commonly is because x is equal to u over n. And this can cause complications. That means that you're leaving this out in the integral, and you just have a bunch of ambiguity and complications. So that's why u equals x to the power of n is a lot safer. So here we're going to need to do this because we have this. Okay, so because of that, we're going to be safe. And I know I'm going to be safe even more because this is an exponent. So u to the power of n is not going to, destruct this whole entire integral. Okay, so let's go ahead and do that u-substitution. Okay, notice that we plug in 0, 0. 1 is now n. Okay, you see how this can be a little dangerous, but of course we should be okay because we do have nx supporting us. So n, that's canceled out. We have now sine of e to the u over n. and then 1 plus u squared. Okay? Can we compute the infinity now? Is it safe? Yes, it is, because now this is u over infinity. This will be 0. This is going to be like, what, sine of 1? Yeah. From 0 to infinity, we have sine of 1. And we have 1 plus u squared du. This is safe. We are safe. So this integral is equal to pi over 2 sine of 1. Okay? And there we go. We're done. Alright, we solved the limit integral. So again, I know this whole lesson looks exciting. It's like, oh, okay, we're getting to some interesting, cool stuff here now. Yes, this is some very satisfying stuff. But remember that this is limit integration. So not only we're entering some most fun, but we are entering some most dangerous territory of integration techniques. Okay? So we're like this close to like the death of divergence. So just be very careful. Don't go too crazy. Alright, let's do another example. Alright, we have another example here. We have nxn times e to the x squared dx. Okay, interesting. We know that ex squared is, we can't really integrate that. But we have this that might help us modify this into something easier. So that u equal xn, then, well, dx is technically going to be equal to 1 over n u 1 over n minus 1 du. Okay, so now you go ahead and apply that substitution straightforwardly. 0 to 1, n cancels out. That's u. E to the x squared is now going to be 2 over n. U 2 over n. And then times u 1 over n minus 1. This cancels out with this. And now, can we plug in infinity? Yes, we can. So when we plug in infinity, we get, this is 0. So we get e, and this is 0, this is 1. So I guess this whole integral just simply equals to e. Alright, so this is our last limit integral in this section. So we notice that we have an even function, so let's just go ahead and simplify that first. So using symmetry, we have this going from 0 to infinity, and now we have 2n sine of x to the power of 2n dx. Now, I see that we have an n at the front, so clearly we're going to have to do x to the power of 2n u-substitution. And then this is going to be u 1 over 2n equal to x. And so this is going to look like this. U 1 over 2n minus 1 du equal to dx. And so what we have left now is that we now have a limit of 2 from 0 to infinity. Right? So from 0 to infinity. And then we have, let's see, that 2n's canceled out. We have sine of u. And then we have our our dx is going to have that minus 1 is this. And then times u to the power of 1 over 2n du. Now, are we safe to plug in this limit from n approaches to infinity? Yes, we can, because it's just this. So 1 over infinity, that's just 0. So, as you can see, we clearly have a Dirichlet integral, sine of u over u du. Cool, so now this is equal to 2 pi. Okay, and that's it. Alright, that's our last integral. Not too bad. Was actually quite nicer than I thought. But yes, these are limit substitutions. It takes a while to get used to. Sometimes it's not always u equals x to the power of n. It could be other things too. depending on the integral function. So yeah, it takes a lot to get comfortable, but it is definitely one of the most fun things to do in limit integration. Okay, so definitely rewatch this video to practice these problems on your own and getting comfortable with them. Other than that, I hope this helps. Thank you so much for watching, and I'll see you guys in the next part.